So in the last video, I outlined some gamma function related formulas, and now in this video I'm going to prove them. So first off, we're going to start with Stirling's approximation. That's gamma of n plus 1 is asymptotically equal to square root of 2 pi n times n over e all raised to the n. So basically this is like equivalent to n factorial for large n, so you can use it in limits pretty much. So we're going to start off with gamma of n plus 1. This is just equal to the integral from 0 to infinity of t to the n e to the minus t dt. And I want to rewrite this using the properties of exponentials and logarithms. We have integral from 0 to infinity of e to the n ln t minus t dt. And now we're going to consider a substitution. The substitution is going to be u is equal to t minus n. If we do this, so first we're going to get a 1 over e to the n factored out, but then we also get an n to the n. I'll explain where that comes from. So we have overall n over e to the n. Now the bounds changes from negative n to infinity of e to the n ln of 1 plus u over n. So basically I factored out an n from inside of this logarithm and it came out as n to the n, right? And then minus u du. And now with this, we want to write this as a power series, what's inside the exponential, because this is going to be useful when we take the limit. But so this is just going to be n over e to the n, integral from negative n to infinity of e. Okay, so for ln 1 plus x, that's a common one. Here we just have u over n. Now for the first term, what we're actually going to get is u over n, right, times n. So that just becomes u, and then we subtract u here. So the first term is just going to cancel out. So all we care about is the terms afterwards. So that's going to be minus u squared over 2n plus u cubed over 3n squared and so on du. And now with this, we want to consider another substitution. This substitution is going to be v is equal to u over square root of n. So we're going to get a square root of n factored out times n over e all raised to the n. Then the bounds change. We have negative square root of n. This is still to infinity. And if we look at e here with our Taylor series, our Maclaurin series expanded, we're going to notice that the first term is going to simplify to be only in terms of v. So we have minus v squared over 2, then plus v cubed over 3 root n, and so on dv. And now what we're going to want to do is take the limit as n goes to infinity, but actually I'm going to rewrite this as asymptotic equivalence. For asymptotic equivalence, we don't care what we already have factored out as constants. We only care what happens to the integral, right? So we're going to take the integral. This is as n is approaching infinity, right? And so now this is going to be square root of n times n over e to the n. And now notice that from the Maclaurin series, from our power series expansion, everything else except for the first term has a factor of n in the denominator, right? So when we take the limit as n goes to infinity, those are simply going to cancel out. They're going to go to 0. So we're going to have the integral from negative infinity to infinity of just e to the minus v squared over 2 dv. Now, there is one more substitution we need to make here. So if we just do x is equal to v over root 2, then now we're going to get root 2n So the root 2 comes out, n over e to the n, integral from negative infinity to infinity of e to the minus x squared dx. And now you know that this is the well-known Gaussian integral. And so we're just going to get square root. So we get square root of pi from that. So we get overall square root of 2 pi n times n over e to the n, as we were expecting. So that's Stirling's approximation. Now I'm going to prove the beta-gamma relationship, which is that beta of x and y is equal to gamma of x times gamma of y over gamma of x plus y. Now, looking at the definition of the beta function, so this is the integral from 0 to 1 of t to the x minus 1 times 1 minus t to the y minus 1 dt. Now this looks a lot like a convolution, which is another way that we can multiply functions, where basically you get another function that tells you about how the shape of each function affects the other, right? And this plays really nicely with Laplace transforms. And so this one specifically for a truncated domain, like it is for the beta function, we have f convolved with g is equal to the integral from 0 to t of f of tau times g of t, times g of t minus tau dt. And so this looks a lot like the convolution if we considered f to be t to the x minus 1 and g to be t to the y minus 1. So how about we plug this in and see that this is going to give us the integral from 0 to t of tau to the x minus 1 times t minus tau to the y minus 1 d tau. Sorry, here I forgot to say this was d tau, not dt. Okay, so now what we want to consider is a substitution. So if we let u to be equal to tau over t, then we're going to get some nice simplification. Basically, we're going to get three pairs of t's here, one from the changing to the du, right? Then the others from these pairs of exponents. So overall what we're going to have factored out is t to the x plus y minus 1 times the integral from 0 to 1, right, of u to the x minus 1 times 1 minus u to the y minus 1 du. And this is just equal to t to the x plus y minus 1 of the beta function of x and y. So now we know that basically, so this convolution, we have this result in relation to the beta function. Now the beta function here is pretty much like a constant value because it doesn't depend on t. So again, this has a nice relation with the Laplace transform, that we can break the Laplace transform of f convolved with g into a product of the Laplace transform of f times the Laplace transform of g. So what we're going to have is the Laplace transform of t to the x minus 1 times the Laplace transform of t to the y minus 1. And again, so the beta function is a constant, we can just take this out. So the beta function times the Laplace transform of t to the x plus y minus 1. So now if we go along with this, again, you could pretty much just consider for like t powers here, consider looking at the pattern, or you may also notice that we kind of covered the Laplace transform of this based on the gamma function in the previous video. But basically what you're going to get is, if you again look at patterns, So you're going to get x minus 1 factorial over, this is over t to the x, and then we're going to get y minus 1 factorial over t to the y. And so this is going to be equal to the beta function, and then times, again, similarly here, we're going to have x plus y minus 1 factorial, and this is going to be over t to the x plus y. Now notice that, again, because of the properties of exponentials, we can bring these two together as a sum of t to the x plus y. So what we have is that these denominators are going to cancel. So now we have an expression just for the beta function in terms of factorials. So if we rearrange this, we're going to get beta function of x and y is equal to x minus 1 factorial times y minus 1 factorial, all divided by x plus y minus 1 factorial. And again, you can simplify this using gamma functions. This is just going to be, as we expect, gamma of x times gamma of y, all divided by gamma of x plus y. And that is what we were looking for. Moving on, there's the Euler representation of the gamma function, which is gamma of z is equal to 1 over z times the infinite product, and is equal from 1 to infinity of 1 plus 1 over n all to the z over 1 plus z over n. So we're going to start off considering a limit, which is a limit as n approaches infinity of n factorial times n plus 1 to the z over n plus z factorial. Now this can be shown using Stirling's approximation that this is equal to 1, and that's also if z was a real number, but we're going to consider the unique extension for complex numbers, so we're going to say z is a complex number, right? Now with this, what we're going to do is I'm going to multiply both sides by z factorial. So z factorial is equal to the limit as n approaches infinity of n factorial times z factorial times n plus 1 to the z divided by n plus z factorial. And now I'm going to expand the factorials as products and also rewrite n plus 1 as a telescoping product, which is basically where numerators and denominators of a product are going to cancel out. Basically, it's still going to be n plus 1, but we're going to have, so the limit as n approaches infinity of, now I'm going to write factorial in ascending order now. So we're going to have 1 times 2 times and so on to n, and z factorial over n plus z factorial. We can already just rewrite that as another product, which is, what we're going to have is just, so 1 plus z times 2 plus z onwards to n plus z, right? And now for the n plus 1 to the z, so let's consider, so if we have n plus 1 divide by n and multiply by n, this is still going to be the same thing. Now, what if we keep doing this with lower factors, right? So this just keeps going on like this until we get to basically 3 over 2 times 2 over 1. So again, because of the way that the numerator and denominators are going to cancel, this is still n plus 1, but we can rewrite it as this product. So what we're going to have is 2 over 1 times 3 over 2 and so on to n over n minus 1 times n plus 1 over n, and this is all raised to the z power. And now with this, we can just basically take this to be an infinite product. So we have z factorial is equal to, so the infinite product, n is equal from 1 to infinity. Now, so for this part over here, we can write the term as, again, n plus 1 over n pretty much, right? But normally what we do is we split up the fraction, so we have 1 plus 1 over n, and this is still raised to the z. And now from this part over here with our factorials, right, if we just there's still n terms in each of them, or n factors in each of them, so if we divide each by 1 corresponding on the numerator, then what we're going to get is 1 plus z over n, right? And now we know that z factorial is equal to gamma of z plus 1. So gamma of z plus 1, by the functional equation, that's z times gamma of z. So then we know, well, we can already write it now. So if we divide by z on both sides, then we're going to get what we want. So gamma of z is equal to 1 over z times the infinite product, n is equal from 1 to infinity of 1 plus 1 over n to the z. And then we're going to divide by 1 plus z over n. And now this can also still be kept in terms of a limit, basically. So if we want to, we can also rewrite this as 1 over z times the limit as n approaches infinity of n to the z times the product of k is equal from 1 to n of k over z plus k. So both of these are valid, and sometimes considering it as a limit is also more useful. But anyways, we got what we needed from this. For the Weierstrass representation of the gamma function, it's pretty much just a restatement of Euler's definition as an infinite product. So that's going to be gamma of z is equal to e to the minus Euler-Mascheroni constant times z divided by z times the infinite product, n is equal from 1 to infinity of e to the z over n divided by 1 plus z over n. So we're actually going to start with the Euler's representation, and it's going to be the limit form. So we have gamma of z is equal to 1 over z times the limit as n approaches infinity of n to the z times the product, k is equal from 1 to n of k over z plus k. All right. Now, again, we are going to rewrite this using some some exponential identities, right? So we basically want to get e to something with a logarithm, and then we're going to try and squeeze the limit for the Euler-Mascheroni constant in eventually, and whatever else happens in the product. So this is just going to be, so we're going to have 1 over z times the limit as n approaches infinity of, so e, n to the z, we can write this as e to the z times ln of n. And then from the product, we want to consider the reciprocal of what we have. it's going to still maintain the same thing, but we're going to consider its reciprocal and then raise to the negative 1. So that's just going to be, so from k is equal from 1 to n, we're going to have 1 over 1 plus z over k, right? So this already looks familiar, right? And now let's try and force the harmonic numbers in here, basically by like adding and subtracting it. So if we have here, we have 1 over z times the limit n approaches infinity of, so we're going to have e to the, now I'm going to, instead of just adding and subtracting the harmonic numbers themselves, and since we have a z here, it would be nice to be able to also factor that out. So I'm going to add z times the nth harmonic number minus z times the nth harmonic number. So we have z times h of n minus z times h of n, and this would be now plus z times ln of n. Product stays the same. K is equal from 1 to n of 1 over 1 plus z over k. And so now we can isolate a product where we're going to get basically the e to the z over n, and then there's also going to be the Euler-Mascheroni constant, right? So we're going to have 1 over z times the limit as n approaches infinity of, so we're going to have e to the, and now I'm going to write this specifically, the harmonic number, as a sum here, like we have k from 1 to n of z over k, right? And then again, due to the properties of exponentials, now we're going to have e to the minus z, and then times h of n minus ln n, which is what we are kind of looking to get from this. And then we have the product, k is equal from 1 to n of 1 over 1 plus z over k. Now with this, we can rewrite e to the harmonic number, to the nth harmonic number, we can rewrite it as a product. So we have, basically, we have the product of k is equal from 1 to n of e to the z over k, right? Because e to the sum is just the product of e's. And then we have this times e to the minus z, nth harmonic number, minus ln of n, times the product, k is equal from 1 to n of 1 over 1 plus z over k. And now, since these two have the same bounds, we can just bring them together. So we're going to have 1 over z times the limit n approaches infinity of e to the minus z h of n minus ln of n times the product, k is equal from 1 to n of e to the z over k over 1 plus z over k. Right. And now applying the limit, so we're going to get an infinite product, and then because of this relationship here, again, you can basically pass it through the exponential and the minus z, right? Because those are just, so e is obviously like continuous at n approaching infinity, and then the minus z is just a constant that comes out. So then we are going to get our e to the minus Euler-Mascheroni times z divided by z, and then again, so the finite product becomes an infinite product in the limit. K is equal from 1 to infinity of e to the z over k over 1 plus z over k, right? So this is what we were looking to prove. And now technically here I used different bound. Instead of n I used k, but again those are just dummy variables. They could be whatever you want. This is still valid. Okay, so I forgot to say this in the last one, but I'm not going to show the proof for the Hankel form of the gamma function as a contour integral. But again, you could probably just do that yourself, again, interpreting it as an inverse Laplace transform. But moving on, we're going to get to the formula. So the reflection formula, right? Gamma of z times gamma of 1 minus z is equal to pi over sine of pi z. So for this, what would be useful to consider is any one of the infinite product representations of the gamma function, right? Because I also showed you the Weierstrass products of sine, and basically this is going to pop up in our evaluation. So I think what's easier to do is to consider the Weierstrass factorization. And so if we do the Weierstrass factorization, then we're going to have gamma of z times gamma of 1 minus z. Then this is going to be equal to e to the minus Euler Mascheroni times z over z times the infinite product, n is equal from 1 to infinity of e to the z over n over 1 plus z over n. And then gamma of 1 minus z, using the functional equation, we can just factor out a minus z, so that's the same as minus z times gamma of minus z. So we can have a minus z here times e to the, now this is positive, Euler Mascheroni times z over z, right? And then we have the product, n is equal from 1 to infinity of e to the minus z over n over 1 plus z, oh wait, sorry, this is now negative, so 1 minus z over n, right? And so, oh yeah, this is also negative here, but anyways, so you're going to see these cancel out to just give us 1. These also cancel out. And now, if we bring the products together, you're also going to see that the e to the z over n times e to the minus z over n are also going to cancel out. And so what we're going to get is that gamma of z times gamma of 1 minus z is equal to 1 over z times the product, n is equal from 1 to infinity of, so 1, because those cancel, of 1 plus z over n times 1 minus z over n. And now you may notice that this is basically factored as difference of squares, so we can expand that. So then we have 1 over z times infinite product, n is equal from 1 to infinity of 1 over 1 plus z squared over n squared. Now, again, consider a slight modification of the Weierstrass factorization of sine. So basically, if we plug in pi z, then we're going to have sine of pi z is equal to pi z times the product, n is equal from 1 to infinity of 1 plus z squared over n squared, right? And so this basically is like the reciprocal of that, but there's no extra pi on the bottom, so what we need to do is multiply by another pi on the top. So what that tells us is of course that gamma of z times gamma of 1 minus z must be equal to pi over sine of pi z. And that is the reflection formula. For the last one, it's the duplication formula, which is gamma of 2z is equal to 1 over square root of 2 pi times 2 to the 2z minus 1/2 times gamma of z plus 1/2. Now the beta function here is pretty useful. Specifically, if we do beta of z and z, that's going to be gamma of z, or like gamma squared of z, divided by gamma of 2z, because z plus z is 2z, right? So we have gamma squared of z over gamma of 2z. This is going to be equal to the integral from 0 to 1 of t to the z minus 1 times 1 minus t to the z minus 1 dt. And now we want to consider a substitution. So we're going to let u to be equal to 2t minus 1, which also tells us that t is equal to 1 plus u over 2. And then du is just 2 dt, right? So now if we plug this in, what we're gonna have is, so we're gonna get 1 over 2 times the integral, now this is from -1 to 1, of 1 plus u over 2 to the z minus 1 times 1 minus u over 2 to the z minus 1 du. And we can rewrite this if we multiply these out, and then we're going to get another factor of 2 out. So what we're going to get is 1 over 2 to the 2z minus 1 times the integral from -1 to 1, and then the 1 plus u over 2 and the 1 minus u over 2 to the z minus 1, we're just going to get 1 plus u squared to the z minus 1 du. Now, for this, I'm going to rearrange some stuff. So we're going to have 2 to the 2z minus 1 on the other side times gamma squared of z is equal to, now we're going to have another factor of 2 out here because we're going to rewrite this, since this is an even function, the integral from 0 to 1 of 1 minus u squared to the z minus 1 du. Now if we consider one more substitution, we're going to let v to be equal to u squared, right? And then dv is just 2u du. Again, this is also u is equal to root v. And so if we plug this in, again rewriting the other sides, 2 to the 2z minus 1 gamma squared of z, and again we're going to have another 2 cancel here, so we have gamma of 2z, and then so we have times the integral from 0 to 1, and now we're going to have 1 minus v to the z minus 1, obviously from here, and then from the other factor here from getting our dv, we're going to divide by square root of v, but we can also rewrite this as v to the 1/2 minus 1 times 1 minus v to the z minus 1 dv. And so this is just another beta function, right? There's just another beta function, so we get 2 times 2z, 2 to the 2z minus 1 times gamma squared of z is equal to gamma of 2z, and this is the beta function at 1/2 nz, so that's what we have here. And then again, this part over here is just going to be, so gamma of 1/2 times gamma of z divided by gamma of z plus 1/2, right? And so I'm going to have to move this around. what we have here are two common gamma of z's now, so we can cancel those, right? So we're just going to be left over with 2 to the 2z minus 1 gamma of z is equal to, and so gamma of 1/2, that's just square root of pi, right? So we just have gamma of 2z times the square root of pi over gamma of z plus 1/2. And now we can rearrange so that we're going to get gamma of 2z is equal to, so the square root of pi goes on the bottom, this goes on the top. We're going to have, so we can rewrite 2 to the 2z minus 1 as 2 to the 2z minus 1/2 minus 1/2. So we're going to have a factor of root 2. And then we divide by the root pi, so we have 1 over square root of 2 pi. This is 2 to the 2z minus 1/2. And then again, continuing here since I don't have much space, but multiplied by gamma of z and gamma of z plus 1/2. And that is the duplication formula. For the multiplication theorem, the more general case, it isn't necessarily that much longer, but I'll leave that to you if you want to try and prove that yourself. I'm just saying that the Euler definition of the gamma function would probably be useful to consider. Anyways, that's it for the end of this video. I hope you enjoyed and now understand more where these formulas come from, and I'll see you in the next video.